One of the most important set constructions is called the Cartesian product. Sometimes people just say product, but in other advanced areas of mathematics, there are other kinds of products. So it's better to be specific and say Cartesian product. And it underlies everything to do with relations and functions and images and big data. So this is a construction that gets used over and over and over again, and so it's important to understand it. It's very important to understand the concept of relation and function, and you can't understand these until you have an idea of what the Cartesian product is. So we have two sets, and we're going to not specify much about them because this is an abstract subject. In the big data situation, you'd have 30 sets or something, and they would have certain properties, but we'll start with two. And so we have sets A and B, capital letters, and we have a very strict definition of the Cartesian product as follows. Usually people say A cross B, so there's the notation, and it's a set, and we're going to specify how to construct that set. Usually A and B are too big to do rosters, and so we specify the test that must be done. So this is actually kind of a parameterization. So it's the set of ordered pairs, little a, little b, where little a is in big A, and little b is in big B. So this is the strict definition of the Cartesian product, and when all else fails, you go back to this and see what's going on. So everything in here is an ordered pair, and the order matters here. A and B themselves may not have order, but these pairs have an order. The first one comes from A, the second one comes from B. In many cases, A and B are the same set, but not always. If A and B are the same set, and we want to talk about A cross A, people use a superscript 2 and call that A2, not A squared, A2. So we'll go on from there. I'm trying to get that visible. Okay, so that's the basic situation as far as the definition goes. So if you wanted to pick a typical element of the product A cross B, that would be a pair A, B. And there we go, okay. Sometimes it's really advantageous to represent these with, it's like a graph. It's not quite a graph because there may be no order to A and there may be no order to B. But we can, if we pick a certain element of A and some element of B, that does define a point that has two coordinates. So we think about that kind of metaphorically as being a graph. And so there's AB. Actually, if you draw a graph that defines a subset of A cross B, but we'll get into that in a little bit. Okay. This picture becomes very unwieldy if you have more than two sets because you add a dimension, literally add a dimension for every set that you have. So if you have three sets, A, B, and C, and you want to look at A cross B cross C, then that needs a third dimension, which would be coming out from the page. And most people have a lot of trouble drawing that. And four sets would require a four-dimensional picture, and almost everybody has trouble drawing that. But so we kind of stick to this situation. Okay, so I mentioned A cross B cross C, and what that is a set of ordered triples. So they'd be little a, b, c, and each little letter comes from the set with the corresponding big letter. And one of the reasons we do this is taking me a long time to write out, but there's the definition of A cross B cross C. There's something very important that you need to be aware of. And this is being very, very picky. But in these abstract realms, if you're not picky, you're wrong. So if we look at the following set, A cross B cross C, where I've used some parentheses. And so this is a set of ordered pairs. The first one comes from A, and the second one comes from B cross C. I've constructed B cross C some other time, and now I'm picking some element of that. So this looks like the first pass is to say this is a set of pairs AX, where little a is in A, and X is in B cross C. That is not very satisfying. It is very difficult to prove or compute with this kind of definition. And so it's immediately seen to be much better to say that this is, now you got to be very careful here. You got to say this is A comma something, because A cross B cross C is a Cartesian product. And the something here is the ordered pair BC. And again, we have the same conditions, A and A, and B, and C and C. The parentheses matter. Someday you might get to do some Lisp programming, LISP, and you'll realize parentheses really does matter. So Lisp is a non-functional language that was very popular in the early days of AI, before we knew how to get data. And so the big deal here is that if I take A cross B cross C, that makes perfect sense. You just take one from each slot. This as a set is not equal to the set A cross B cross C. This should bug you, and until it stops bugging you, you'll get things wrong. You have to strictly go by the definitions, and the definitions here, one is a set of triples, sets of three things with an order, and the other is a set of doubles, one of which happens to be a double. So these are different things. Now, this is something that we're going to address in a little bit, not today, but they're obviously very closely related. And in teasing out that relationship, you'll be able to come to appreciate and have some tools to work with other sets that are useful. So these are equal but closely related. It's kind of like getting an email from Ancestry.com. Okay. Now, one of the other first things that you do with sets is look at the size, and this only applies to finite sets. But the size of A cross B is this is fairly simple. This is just the multiplication rule. You choose something from A, so the number of choices is the number of things in A, and then completely independently you choose something from B, so the number of choices there is the number of things in B. So this is just the size of A times the size of B, and this is just the multiplication rule that we did way back when. And so that works out to be pretty nice. Now, if you want to mess your mind up a little bit, let me write something down and then I'll say it out loud. This is, you got to read this stuff super, super, super carefully. This is the paper and pencil equivalent of bit twiddling. So here's a true statement. I guess I could say that's a theorem. And so this says that the size of A2 is the Cartesian product A cross A, is the size of A squared. So one of these superscript 2's is a 2, and one of these superscript 2's is a square. I'm sorry, I have no further comment on that. You just have to read it very carefully. And so there's the situation there. One of the things that can help you understand what's going on with these products is to look at some subsets of Cartesian products. And so these come out or turn out to be very important in all kinds of areas of mathematics and computing. So let me look at subsets of A cross B. And so we'll look at some examples. And the first one is this, and I'm going to call the subset S. So S is the set of all ordered pairs AB, where A is less than B, and this is a subset of the natural numbers cross itself, or N2. So that's the setup here. So I've got a bunch of pairs. So A comma B is an element of A cross B if A and B are they're both the natural numbers. So I guess I should write that down. So usually, if you already have a symbol for a set, you don't introduce a new symbol that has the same meaning unless you're trying to bamboozle somebody. So, but I have written down that A is the set of natural numbers, B is the set of natural numbers. And so, but what I've said here is that these ABs are in N cross N. So A has to be a natural number, B has to be a natural number. And the subset's defined by this rule, whether A is less than N. And one of the things that you can do that may or may not be helpful is to try to draw a picture of this, and it very quickly gets out of hand. So for example, when A is 0, then everything that's bigger than 0, so that's starting with 1, is in there. So I've picked a spot where A is 0. Now there is an order to the natural numbers. I'm taking advantage of it. So A is 0, and then 1, 2, 3, 4, 5 are in there. That's when A is 0. When A is 1, we'll do it with different colors, see if we can see what's going on. Then the acceptable B's they have to be bigger than 1, so 2, 3, 4, 5. So we get a picture kind of like this. This picture is kind of hard to draw, but that's the situation. And then let's look at one more. When A is 2, then the smallest B that works is 3, so we get this picture. Not very helpful. Not unhelpful, but not very helpful. So let me give you kind of as an inset another version where I'm going to let's go out, instead of going 1, 2, 3. Let's think big and go out to 10 to the 6th, go out to 1,000,000. And now what you're seeing here is that this subset S looks like this. I'll just kind of shade it in. Well, first I'll label it, and then I'm going to shade it in. So that's the big picture. So it's this kind of triangle that goes above the diagonal. So, but that's a subset of N cross N. I've drawn it so small that the little bits of ink that indicate the points have kind of bled onto each other. And so it looks like a solid region. It's not, but it looks that way. But this kind of gives you a big picture of the this less than relationship. And it's this is very common in a lot of analysis of computer science algorithms to use pictures like this. So this is something that you will see again. Okay. So that's one example. There's another example that is very telling, which is this. I guess I'm going to call this Q, not rational numbers Q, but just Q. And this is the set constructed as follows. So, and again, I'm going to use the natural numbers because everything in computing comes down to natural numbers. So this is going to be a set of ordered pairs. And the first entry here is going to be A. So far, so good. Now, but wait, I've only specified one set here. So what's going on? And that's because I'm going to make the second component, the second part of the ordered pair, a function of A. So I'm just going to use A squared. So I have 1 point in this set for each natural number, and this is a subset of n cross n. That's very important. Sometimes when people are running out of space, they write the subset symbol vertically instead of horizontally. So I'm saying that this set here, this set Q, is a subset of n cross n. Now, if I start to make a picture like this, where you're gonna the dots disappear off the top of the page really quickly because squaring grows so quickly. So what I'm going to do is make kind of a large scale picture where I'm going to go out to 10 to the 6th. And the picture, it's dots. There's something over 1, there's something over 2, nothing in between, something over 3, something over 4, something over 5, something over 6. Ow, I almost threw my shoulder out trying to reach that. Anyway, it looks like a parabola. It's not a parabola because a parabola is a continuous curve, but this is made up of a lot of little dots. The thing is, the dots are so close together that they kind of merge, and so it looks like it's continuous, but it's not because we've specified the natural numbers. So again, this is a subset of n2 or n cross n, and then we can start to talk about some of the properties of that subset. So, but these are the common ways of constructing subsets of Cartesian products. One is to specify a rule that they have to have, or the other is to take one. This is like with functions. This works out pretty well. This is what a function is. We'll talk about that soon. And then you have to be strict with the definitions. But this is one of those constructions that you use almost daily in doing computing and many times a day in doing math. And so it's worth spending some time on.